And so if the particles have no attraction to each other, or sorry, they do have attraction to each other, and we're assuming they don't, then particles, when they're spaced out from each other at low pressures, that assumption of them having no attraction to each other gets a lot better. And so you'll see at very low pressures, um, gases seem to behave like ideal gases. And as the pressure increases, they deviate from it. The same is true for temperature. So this is Kelvin. So 298 Kelvin is 25 degrees Celsius, and 873 would be about 600 degrees Celsius. And what they're showing that is as temperature increases, the particle seems to the assumption that they're an ideal gas gets better and better. Okay, so if this kept going up, if I perform this at, say 1200 Kelvin, the line would start to approach the ideal gas. And why that makes sense is because, like if you've ever dealt with magnets and you're moving them really fast past each other, that is to say, when you're moving them really fast past each other, you're simulating high temperatures, and they don't have time to stick to each other or even have time to interact because they're just moving so fast. They have so much kinetic energy that you can't get them to stick together. And so if it's really high, the kinetic energy of the particles is far, far, far greater than the attraction between them. And so you get deviations of ideal gases. And then when you go to uni, this last part is definitely uni. This is all stuff that you need to know. But just know that there's a correction formula. And this is actually called van der Waals equation. And essentially there's fudge factors, I guess, to account for intermolecular forces that we learn about. So the attraction between particles. Intermolecular forces is something that you learn about in module 1. It's really, really key to the course. And this one here, this fudge factor, B, is to do with the size of the particles. So there, if you want to start figuring out the volume and pressure of gases at different temperatures and pressures, you actually need to factor in all this kind of stuff. This does not take away from the mole concept. This is just dealing with gases and worrying about how they interact and what size volume they occupy. The mole concept is still extremely accurate. Remember that mole concept does not just rely on the box and gas form. There's heaps of different methods. What it does tell you, though, is if you're going to go physically do all these things, you need to kind of, if you go get a 25 litre box, as I've been talking about, this 24.79 litre box, you go, well, that's at low pressure. So my assumption of it being 1 mole of particles is pretty good. However, if I'm starting to do that at, that was just for pressure, but I realized that that's at fairly low temperatures. And you can see at these fairly low temperatures, the green one, it's okay at low temperatures. It's an ideal gas, but as soon as I go to high pressures, it's going to deviate from that. Probably not well put, but what I was just trying to say is I need to account for pressure and temperature and understand that it can deviate from ideal gas. So if I'm going to go form calculations and measure out volumes of gases, I need to be on top of that so that I can't just go, 25 liters is definitely 1 mole of particles at every temperature and pressure. I've got to account for this kind of stuff.